Okay, so today we are going to talk about model-based design. One of the main ideas in this textbook, or as the main content in this course, is that we're going to be not only talking about how we program microcontrollers, um, how we design these systems. We're going to also look at in terms of, well, before you actually do the design, what are the things you should consider when you start with the design. So we will look a lot into the model-based methods. So design, you're going to be end up with, start with some models. So today we're going to talk about the concept of model and how that influence the design process. So we're going to talk about model-based design, and we're going to talk about a cyber-physical system example. And I will later introduce the Arduino development flow. And if I have time, I will briefly introduce the first lab. So last week, we talked about this modeling, design, and analysis. As we show in this diagram, these three parts or three stages form a iterative process. Modeling is the process of gaining a deeper understanding of the system through imitation. So when we are given a problem or a implementation or solution to design, we are faced with some actual applications, and these applications have different requirements in terms of the functionality, the performance metrics. Modeling is, in this context, is try to understand the cyber-physical system that we are trying to design for, to build. This cyber-physical system will interact with the physical part of it using sensors and actuators. Also, we will use the cyber portion of it to control or sense the physical environment or physical devices. So we want to have first a model that can specify what a system does. So what will be the LEDs that you want to use to show different colors? How many colors you're going to show, for example? Or if it is a motor, what kind of motor you're dealing with? Is a DC motor, or is a step motor? So what kind of movement you want to generate when you have this cyber-physical system? Then the design part is what we traditionally focus on, which is the structured creation of artifacts. This includes hardware and software. So at this step, you go ahead, pick individual components, hardware components, how to connect them using what kind of buses, and then write software that will run on such hardware systems. So this is where we spend a lot of time thinking about how we build such a system and how we debug the design so it can work to produce the expected results. This stage also includes optimization. You may end up having to change the processor or the memory component or the I/O devices to make it more faster or more energy efficient. So that's the optimization is part of the design stage. And the third stage is the analysis stage. Analysis is the process of gaining a deeper understanding of the system you've built. And it requires sometimes dissection, which means that you're going to be using tools, maybe hardware probes or software, debug or software performance analysis tools to understand the performance of each of these components that in your system. With a good understanding, a deeper understanding of how system behaves, you can figure out whether the design meets the requirement, and if it does not, hopefully the analysis will help you to understand why a system does not do well it's supposed to do. And these three things are oftentimes interact, so it may not necessarily go from modeling, design, analysis, and without any loop back or change of the course. You may end up having to go back from the design phase to the modeling phase to, if you face unsolvable issues, and then you may think about whether the modeling part can be tweaked a little bit to make the design process easier or the cost is cheaper. So that's also a possibility. And for analysis is often very important at every step. You may need to have these quantitative measurements so that the modeling and design can be well informed and guided. So as a start, we will start with models. And models can be represented using many different formats. Oftentimes you want to draw a schematic or some, not necessarily the circuit schematic, but some kind of abstractions that will capture the main physics process or elements, or the interaction between the machine and human. So all these parts can be or should be captured as part of the models. The models will define what are the input signals, what will be the frequency of the input signals, how many sensors there will be, these sensors, what will be their what will be the metrics or the physical physics properties that they will measure. And in terms of the controlling these physical processes or machines, what will be the actuators that you have to have in this system? And in between, you of course have your computational components, maybe networking components to connect these different elements. In the first example, as you can see here, this is a kind of signal processing, signal generation and processing model. What will be the input signal, where we'll apply filters, how we control the power output, how we output the power spectrum, etc. So these are, some examples that show that we should get a good understanding of the cyber physics system that we want to build, and start with this kind of abstractions. The abstractions will give you a lot of information about, when you get to the design stage, what are the components you have to use. Is it going to be a very low-end microcontroller, or do you have to have a microprocessor that is able to run the operating system? So that will, these kind of selections in the design phase will be heavily influenced by the models that you are working with. So I don't know if you can hear the ticking. This is called a Newton cradle. Some of you may own it or play with it. So this is a physics process. This process is in this example is the target being modeled. And to model this, you can have many methods, but Newton has this Newton's law, I think this third law of motion. Some of you, including me, learned this in college early years. But this really shows how people have been using models to provide an abstraction of the reality here. This model captures the motion, the speed, and how it's going to be changing based on the time, depending on the time. And this, differential equations is a calculus, and it's part of the Newton's laws. The goal here for this example is, of course, we want to use such mathematical models to capture this physics process. And fidelity is how well the model and its target match. So if there's no energy loss in any form, this process can go on forever. But in reality, this will eventually stop because there's, the friction of the air or these coming from the wires. So a lot of things may happen. So eventually, this process will slow down. But still, this model in mathematical format captures the basic principles in this physics process. This slide, I just want to say that the model and target, of course, they're different. So some people will say that, why do we have to have a model? Because this famous person said, Solomon Golom said, you never strike oil by drilling through the map, which is true, right? You won't get the reality that the oil coming underneath the map, but nevertheless, we should start with the map because you can't really do a lot of discovery drilling without a map. So map in this example is a very good abstraction of the geography structure of the Earth, the locations, orientations. So as a good engineer, you should start with the map if you want to find the oil well and start drilling. So what we learn from here is that you should not confuse model with target. We should have models for the cyber-physical system target we're trying to design. Okay, next concept is the determinacy. Determinacy really means that the model or properties are deterministic. The most valuable models, some of the most valuable models are deterministic. Model is deterministic if given the initial state and the inputs, and the model defines exactly one behavior. You can find that this is generally true for many situations, especially for the system you're trying to design, most cases. And that's the ideal case we want to achieve. And in many of these applications, if you have a deterministic model, the design will be easier, especially if you want to bound any conditional, situations, boundaries. Deterministic model will be very helpful. And of course, on the other hand, non-deterministic model may happen, and they have their own property, and they will cause some challenges in the design process. So let's look at this simple cyber-physical system. We are designing this cyber-physical system, which is to sense the environment in a physical plant, and then use some sort of actuators, maybe motors, to change the manufacturing process or any things that this physical plant requires. So if you look at these arrows shown here, so coming from the physical plant, this arrow pointing to the computational platform, you can think about this is some kind of sensor inputs. The sensors will be collecting information and send the information to this computational platform. Could be a microcontroller-based embedded system there. And then there could be multiple computational platforms. One is doing the sensing, the other one is doing the actuation control. And these two parts may not reside physically next to each other. So they could be separated in different regions, different rooms in this physical plant. So we need some sort of network fabric, which we'll talk about, different networking technologies we can use to connect these computational platforms. So you can see here we have a very complete control loop. So we have sensing, we have some computation, and then sending the control signal to another computation platform, and eventually generate the control signals for the actuators. Ideally, everything is perfect. So the computational task is deterministic, and also for the communication part, for the networking, there'll be no delays. But in reality, there are a lot of things could go wrong. For example, the physical noises could cause the sensors to malfunction or send inaccurate readings. And the network fabric may cause packet losses due to the unreliable media, for example, Wi-Fi. And also through the network fabric, there could be unknowable and non-deterministic delays. In the computational platforms, depending on what kind of processors you use, whether you run the operating systems or not, you may have uncontrollable scheduling delays if you have multiple tasks running on the same platform. As a result, the execution time of these tasks on the platform will be unknown or non-deterministic. And for the final control, there could be imperfect actuations of those machines. So we can see from this diagram that the deterministic model may not capture exactly what will happen in the real world. There are a lot of the things can go non-deterministic. But with that said, we still have to have a deterministic model at the start to capture the essence of this system. And without that, you will be shooting a random target. So we saw earlier that example, there could be many non-deterministic, unreliable, unknowable factors, delays in real world. So what we're saying now here is that a model need not be true to be useful. So a deterministic model is a good start, but it may not capture 100% of the real system's behavior. So this quote is very interesting in my opinion. So all models are wrong, but they are useful. So even the Newton's law, the third motion's law, it's mathematically it's very beautiful mathematical equation, but in reality, the physics system may not be 100% follow that. What I mean is that the mathematical equation captures the essence of the physical processes, but any real processes may involve additional factors that are not reflected in that mathematical equation. But still, that equation is very useful. So the what kind of models should we use? Let's look at some successful models from the cyber and physical world. Software is a model. The reason we say that is software is a good abstraction of what your computational systems can do. If you have a physical system, based on any kind of processors or microcontrollers, plus its peripheral components, you will need to write code that will run on top of this physical system or this physical processor. So what you see here on the right side is the model in the format of a few lines of code. Of course, you have to map this onto this physical system using software tools, compilers, and loaders, etc. But what this can allow people do is we will have a way to provide an abstraction of the processor so that the programmers, the developers of the software, like you guys, you don't really have to personally build this computing system, this circuit board or even the processor. You can just follow this high-level language syntax. This could be, I think, like a Java code. And this Java code will be able to execute this algorithm on this processor. And when you write the software, there are a lot of things you should consider. One of them is a single-threaded program or a multi-threaded or parallel program. If it's a single-threaded program, like we showed here in this example, and chances are this kind of programs are deterministic models. Because when you execute this program from its entry point, from the first line in this program, the execution will follow precisely the logic that you implement using this high-level language. You have a for loop, and then you have some if statements and another if statement, then a nested for loop with if statements. These syntax, these lines will be followed exactly at runtime based on of course, the values of these variables. You don't expect that this program will produce you non-deterministic output as long as your input is deterministic. The reason we emphasize the single-threaded because when you have a single-threaded program, you don't have any variables that will be affected by other running instances, like another thread or another processes. When you have multi-threaded programs or parallel programs, and when you share variables, and that's a different story. And that's where the non-deterministic or non-determinism will come in, because each run of the same program may lead to a different timing-related sequence of these variables. The values will change depending on the time. So your execution flow will be affected. If you have a single-threaded program, then you can confidently say that the execution path will be deterministic. So that's what I want to say about this software as a model. It's a very interesting concept. I think you should understand this is what you can view, and when you pursue any cyber physical system designs. This shows a little bit more about what I just said, the single-threaded program. This program defines exactly one behavior given an input x. So based on the value of the x, if it is greater than 1,000, it'll become 1,000. If it is positive number, it will go into this if statement. Otherwise, it will stop. So this example is a C language implementation. This software model or this language defines the behavior and also the input. When we have this deterministic program, single-threaded, the target of the model is actually non-deterministic. How we understand is that, because in the physical process, when you apply current to this computer board with this processor, the electrons running through the silicons, their behaviors are non-deterministic. That this is at the very lowest level of the hardware that we are observing here. Then you may ask, oh, so if that's the case, how do I guarantee that my program will be executing and producing the expected behavior, the expected outcome? It is because we have several other layers of abstractions of this hardware on top of this electrons. You don't expect that this C program to map to these electrons directly. You actually have a lot of intermediate layers or abstractions. For example, instruction set, and then this architecture of the processor, the pipelining, and the microarchitectures, all these internals designs of this processor. This is where I was, talking about the another layer of deterministic model that abstracts the hardware. So given the physical system, although it is true that the electrons move around non-deterministically at the atomic level, but on top of that, we have several layers of abstraction. And this is the model at the instruction layer. This is the instruction set architectures, or ISAs. ISAs are abstractions of microprocessors or microcontrollers. Every processor, as long as it's programmable, it defines certain type of instruction set. There are several main, two main instruction set. Do you guys know? Two main categories.
RASK.
RASK.
RISC, my bad.
That's right. So you're right. That's one of them. That's shown here. There's another type. It's kind of the opposite to the RISC.
Complex. CISC?
Yes, so CISC. So complex instruction set. Very good. So can you tell me a example of risk-based processor?
ARM?
Good. What about CISC-based processor?
x86.
That's right. So x86. So those two are, I would say, probably the most popular two instruction set for majority of the processors. So in this example, it's a RISC-based instruction set. The reason we call it RISC is because every instruction has the same 32-bit length as shown here. And on the higher bits, it defines the locations of the registers. So you have 5-bit value to define the destination register, and then 2 other source registers in the register file. And the lower bits defines the actual functionality of the instruction. Start with the upper code, and then follow upper code. We have a 10-bit function field, selects the type of operations. So this is the RISC instruction set. So this is the abstraction of the processor. What this tells you is that as long as you generate sequences of such instructions, your program will be able to execute on this particular processor as defined by these instructions. On the other hand, if it is a CISC type of processor, then the instructions will be different from instruction to instruction. The length of the instruction will depend on the type of the instruction, the number of operands, and type of operands. But either one, either CISC or RISC, the instruction set architecture are deterministic models, and that's why for software you can rely on such deterministic model. No matter how the electrons move, these functionalities will be supported. The instruction set architecture relies on another deterministic model. And this model is basically the circuit level model. So we have a NOT gate and NAND gate, inverters. You have, this is the multiplexer. You have an AND gate, NAND gate, and you have adders. These type of models or schematic is also deterministic. This is the digital logic level, which is going to be implemented at the end on top of this silicon wafer within the chips. And because this synchronous digital logic is deterministic, that's how we can guarantee the instruction set can be supported in a deterministic way. Okay, so we know cyber-physical system has both the cyber side and also the physical side. The physical side is often involves certain physics, dynamics, sensing, or actuation. So any physical system that we interact with follows some kind of physics law. In this regard, what we can also do is to model such physical processes, and we can model this machine using signals going into the machine and signals going out of the machine. And oftentimes these models are continuous models because the physical process is continuous. So you see a lot of differential equations if you model this physical process. And such differential equations are deterministic models, because given input, you expect to have a deterministic output. Okay, so we heard some good news. A lot of models are deterministic from the physics side, from the cyber side. On the cyber side, even though the electrons movement is not deterministic, but the digital logic, the instruction set, the software are all deterministic. But even these several layers are deterministic, but when you combine them, you have now a major problem. What we mean by that is when you have these physical processors, when you have software and you have your physics process and you have your differential equation models to model such physical process. So all these components, these parts are deterministic, but when you combine them, things are getting murky. Things may become non-deterministic. We'll see why that's the case, but the idea is you're going to face a lot of different layers, and also these different systems, they all happen at the same time. So timing, time makes this combination suddenly a very complex, non-deterministic process. Okay, so you know that modern airplanes, you have one pilot or several pilots that control the airplane, but the airplane in the early days, if you saw those movies of war movies, those old machines, twin engine airplanes, they are controlled by the pilot using mechanic or hydraulic controllers. In the modern airplanes now, of course, different. They use computers to control the airplane. So any instructions from the pilot through flip the switches or turn the knobs will be sent to the main controller of the aircraft. The main controller of the aircraft will get these control signals and then change those control signals to actual movement commands to these mechanical or hydraulic machines. For example, change the change the engine speed or the wing angle, etc. And the fly-by-wire concept enables that computers can be used to perform additional checks on these commands from the pilots. So it's kind of mediating pilot commands to double check if these commands are valid or safe to apply. If these commands violate some safety measures. So when you design such a complex cyber-physical system where you want to have this plane aircraft flying safely from your takeoff place to the destination, and you want to be able to still let the pilot manipulate the aircraft and then perform flight that's fuel efficient on time. So all these tasks, all these requirements will make this cyber-physical system a very complex and challenging system to design. What we show here on the left side is not necessarily the systems in this airplane, but what we just want to show that there are different layers of abstractions from the system point of view. You start from the bottom, the physical layer. You have chips. These chips could be FPGAs or microprocessors, and then you may have another layer of abstraction. Or actually, let me start from the top to down. So you start with some kind of performance models and you design hardware description languages, VHDL or Verilog programs, and that maps to FPGA configurations and eventually to FPGA chips. If you design pure software, you may start with algorithms and implement that using C or C++, and then that will be mapped to some kind of x86 instruction binary, the assembly language instructions, and eventually to its binary format and execute it on the microprocessor. So you have very structured, layered design in this process. And of course, that's the ideal case, and we want to use to hide the detailed implementation below that layer. And so the designers can have a simpler abstraction layer to work with. Well, it's not as that clean layer structure for designing an aircraft. The abstraction layer is not as well defined as you have a simple computer system that does one thing. So the collapse of these abstraction layers make the design much more complex and costly. And the design is the implementation if you don't have a good abstraction. So you basically start from scratch. It's like you go back to the days that you want the pilot to control the airplane using mechanics, levers and hydraulic steering wheels like that. So that's really not what we would like to have. So we really need to raise the level of abstractions. You depends on the actual problem. You may have to start with much higher abstraction, not necessarily following exact these layers in this diagram, but you need to have something you can start with to capture the essence of the cyber-physical system. For example, if there's aircraft, you want to set certain minimal speed if the aircraft is airborne. Also, you want to set the minimal altitude for the airplane to be safely moving. So those are something that you need to start with, and you should not just go directly implementing this C or C++ code to control certain actuators. Well, that's where we want to head into. So we want to have higher abstraction so that we can start. So we can start with a abstraction layer that captures the essential requirement. So that's the model we're talking about. But when you go higher abstraction layer, you also have the risk of missing out on the lower level implementations. The example we have here is that the worst case execution time. So WCET here refers to worst case execution time. This war story, shows that because the avionics code from Airbus running on this Motorola processor, Codefire 5307. This processor has a pipeline CPU. Pipeline means that when you have an instruction, you execute the instruction in terms of stages. The simplest pipeline could be instruction fetch, instruction execution, instruction commit. So the actual processor will have more stages than the example I gave here. But the concept of this pipeline is to basically take advantage of the resources on the chip so that you can have more than one instruction executing at the same time at different stages. This will greatly improve the CPU performance. Also, in the processor, especially modern processors, there are data caches. So data caches are on-chip memories that you can store data temporarily. But this caching of data is transparent to the developers, which means that you don't really program your code to have caches storing those frequently used data. Caches are built into these processors. So these pipeline design of data path and the usage of data cache, this on-chip fast memory, will affect the execution time of these individual instructions. So if you say, okay, I execute my 100 instructions, the execution time is, let's say, 100 millisecond. Then you take this as your performance numbers, and think that every instruction, every instruction does the same thing, and that's the universal for every single instruction. Such assumption is dangerous because depends on where the data resides. If the data are already cached in the chip, in this on-chip cache, and of course you can have faster execution time. But if the data are mostly off-chip, then you have to load data from the memory off-chip onto this processor for computation. In that case, the execution time is actually much lot longer than what we saw earlier. So this will affect the worst case execution time that people can assume of. And if your design is strictly timing or required strict timing, like this avionics code for airplanes, then this is something you should be very, very careful about. Do not make such assumptions to say the execution time is guaranteed to be a certain number, because each processor may have different data path and the size of the cache would be different. So that will affect the execution time.